Welcome everyone. So this is our 39th live stream geometry. We have 2 people here with us so far, and I think more people are probably going to hop on later. And today I took problems from 2 different places. So I took 3 problems from the Vietnamese Math Olympiad, and it looks like that contest has some really difficult problems. So we'll see how many we get through. And they usually split each question into a part A and a part B, which is kind of interesting. So I put both the part A and part B for each of the questions. Part B is usually a lot harder. So if we solve part A, but then we get stuck on part B, maybe I might move on to the next one. And then I picked 3 other problems from some random mock contests that I found on the Art of Problem Solving forum. So it looks pretty interesting. And with that, I will share my screen. So here's the first problem. So we have a triangle ABC. So yeah, GeoGebra is starting out a little slow, but I think it usually gets faster as I use it more. There we go. O is a circumcircle. H is the orthocenter. And I'm going to need the point O actually. So O is the center of C. And H is the orthocenter. I might draw the altitudes later. Oh, they say E and F are the theta altitudes from B and C. Okay. So I'm going to want to draw those altitudes. And I might as well also draw the one from A. So E and F. What is D? AH. Okay, so AH intersects the circle at B. And then E and F are the altitudes from B and C. I is the midpoint of AH. So basically the circumcenter of AFEH. Let's rename that. And EI meets BD at M. Okay, so we draw EI and FI. And we want to see where they meet BD and CD. So I'll make the diagram look nicer. Well, that's going to be hard. We want to see where FI meets CD. Oh, you know what? I should have drawn this as a line instead of a ray. We'll do that. Don't worry, I'm going to erase everything eventually. CD should also really be a ray, okay, or a line. So we see where FI meets CD. Okay. EI meets BD at M. And FI meets CD at N. And we want to show MN is perpendicular to OH. All right, so now I'm going to start hiding things.
It's the radical axis of 9-point circle and circumcircle of ABC.
Oh, okay. So because it's the radical axis of those 2, it has to be perpendicular. So we've already solved part A. Yeah, that was fast. All right. I suspect that part B is going to be harder. Just a second. Let me hide stuff. All right. Oops, sorry. This was
FI.
this is EI and the other was FI. Okay, so let me draw the 9-point circle. So that's the circumcircle of EFI, right? That's our 9-point circle. And you're saying these both lie on the radical axis?
Yeah, and this follows from the fact that BDEI are cyclic.
BDEI is cyclic. Okay. So you use power of a point a bunch of times, or just a radical axis?
Cyclicity comes from angle chasing, and after that we use radical axis.
Okay. All right. So that's part A. So yeah, because the 9-point center is the midpoint of OH. So basically we're saying MN is perpendicular to the, that solves it. Okay. Let me draw the 9-point center just to do it. So G is the 9-point center. I know G's usually, maybe I'll just call it K. So for part B, the lines DE and DF intersect the circle at P and Q.
I think we don't need MN anymore. We can hide them.
Oh, they don't have anything to do with the rest of the problem.
The part B doesn't involve MN.
We just need E and F, right? So
yeah, and D.
That's kind of silly. They made the second part of it have nothing to do with the first part. All right. So DE intersects the circle at P. And DF intersects it at Q. And the circumcircle of AEF, which passes through H, that meets, so this is like a well-known, this is the Q point, right? So, so basically if we take the midpoint of, so here's the midpoint of BC, angle AGJ would be 90. So it meets, oh, okay, or angle ARJ, I should say. So this is R. And it meets,
also hide the 9-point circle.
Yeah, I can hide it.
And the circle of BDEI.
Yeah. Okay. And yeah, I'll make these shorter. And I wonder if, oh yeah, by Blanchett's theorem, so arc AQ equals arc AP. Basically, this is an angle bisector. So the circumcircle
really?
of AF.
Actually, isn't it point the intersection of AH and BC?
Label, okay, so I could label that.
What you said is true for that point.
Yeah. So meets it, and it meets okay, this circle meets AO at point S, and we want to show that BP, CQ, and RS are concurrent. All right.
It's a well-known problem that CQ and BP intersect on the midpoint of EF.
Oh, really? Is that by Pascal? It's probably by Pascal, right?
Pascal implies that it's on EF, and projective, from projective we can prove that it's the midpoint.
Okay, so we want to show that the midpoint of EF lies on RS then, right? That's true.
Well, intersection point. Yeah.
Let's see. So yeah, if you draw the midpoint, if L is the midpoint of EF, or we could let them intersect at L and then show that L is the midpoint. Either way would work. So if we let L be the midpoint, and we know that IL is perpendicular to EF, and we know that IL and IL and J are collinear, I think. Yeah. And does the line through IL, so I think IL and J are collinear, right? And it also passes through K, I think. Think so. Yeah. So then we want to show R, L, and S are collinear. Second. One second, guys. Oh, Hakan just joined. Hey, Hakan, thanks for joining us. Let me close this.
You draw the tangent at A.
Okay.
And let it intersect BC. And we project R, L, and S onto BC.
Project R, L, and S onto BC through what point?
Through A.
Okay.
We project T too.
Okay. But we don't know yet that R, L, and S lie on a line, right?
Yeah.
But I guess if they did, then we could project it.
I think what I said is not useful.
Right, it's okay. Maybe inversion might help, because so we want to show R, L, and S are collinear, right? Yeah, we did solve part A. Part A has not much to do with part B. It's kind of interesting. But yeah, Serdar basically saw almost right away that MN is the radical axis of the 9-point circle and the circumcircle. So yeah, part B, yeah, we want to show R, L, and S are collinear. Could we do an inversion about A?
I think inversion makes it easier.
Makes it easier? Yeah. What's the right thing to invert about?
With radius AH.
Invert with radius AH about A, right?
No, AH product by AG. I don't know how to tell it what.
So what's the center of the inversion? Is it A? A.
AH multiplied by AG.
Okay, so it sends H, it changes H and G, it changes F and B, and it changes Z and C.
If we let intersect AR with BC,
AR with BC. Okay.
Yeah. And AL with circumcircle of ABC.
All right. All right. Looks like we have Daniel.
And AO with BC.
Oh, AO. Okay. All
Oh,
right.
it was true. AL also AO. Both of them.
Oh, both of them. Okay. So are we still thinking about doing inversion? Let's see. Let me check the chat.
Intersect AL with
the circumcircle. Okay. So
now we want to prove that ATWB is cyclic.
ATWZ.
ATWV.
Okay. Interesting. Maybe we could use power of a point, AU times UV, UW.
Is TW tangent?
Is what?
The TW tangent.
Oh, let's see. Yeah.
This is through D.
I'm sorry. Yeah, no. T, D, and W are, and E, F, and T are also collinear. Really? And AL is a symmedian. Yeah, AL is a symmedian. So yeah, this is all the Sharkey double configuration, right? Because R is the Sharkey double point. Oh no, I'm sorry, that would be the end circle. Yeah, R is the Q point. Yeah, not the Sharkey double. But yeah, all those properties. So okay, so we want to show that we want to show BPCQ. Okay, so but well, that was the original problem. But then you said we just have to show that R, L, and S are collinear. D, W, and T, yeah, it comes from projective. Let's see. Oh, really? How do you do it? I can calculate angle AWT and angle AVT. Oh, to show it's cyclic. So yeah, so AVT is computable. AWT is the same as AWD. Yeah. So all right. So how did the inversion? So R. So if we invert, it swaps G and H, B and F, C and E. So does R invert to T? Yeah, R inverts to T, I see. And then S inverts to V. Is that? Yes, because angle A. Okay. So yeah, I think I got it. Okay. So I'm going to start typing this up. This is a nice one. I can't believe we solved this fast. But there's still, of course, you said there's that well-known idea that what is it? BP and CQ intersect at L. So I guess we still have to, I'll have to show that when I write it up. Just a second.
How did we prove that TDW are collinear?
That TD and W are collinear?
Yeah.
Oh, I'm actually not sure. I think I've seen it before, but I'll see if I can do it when we write it up. Let me hide a bunch of stuff. Okay, so yeah, let me just do part one really quickly. Okay, so you said D, B, I, and E are cyclic. That's basically an angle chase, right? So for part A, yeah, so I'm just thinking about the fastest way to show that. So angle IEH is equal to angle IHE, and then we could show that that's equal to angle. Okay, so IEH is IHE, is BHD is BDH. And that means that BDIE is cyclic. And for BDEI. And then from there, if we use power of a point, we have MB times MB. Wait a second. So what was? Okay, so it's the same power with respect to the 9-point circle, because I and E both lie in the 9-point circle. I'll say that I, E, and F lie in the 9-point circle. And then we have MI times ME is MB times MD. So that means that M lies on the radical axis. And then similarly, N does also. So MN is the radical axis of those two circles. So MN is and that means that MN is perpendicular to I'll say OK, where K is the 9-point center. And then that means that MN is perpendicular to OH. So that's part A. For part B, so the first thing you said, it's well known that BP and CQ intersect at L, where L is the midpoint.
It's also projective.
Okay. So how does it, is that Pascal's theorem, or?
Pascal implies that the intersection point is on EF.
Okay. So Pascal's theorem proves that they intersect on EF.
And there's a cross ratio proof that L is the midpoint.
Okay. So what's the cross ratio proof?
I don't remember. I will redo it.
Let's see. First, I'll just say BP. I'll see if I can fill that in the end. So,
Yeah,
and I see some. So BP and CQ at L. So I'll prove it later. And then let me draw in some of the extra segments. So we have to prove TD and W are collinear, of course. Are MT and N collinear? I think they are. It's not related to the problem, but it's interesting. That's interesting.
Well, it's because T is on EF and it's on the radical axis too.
That makes sense. So it has to line the radical axes. So, okay, V, and then we drew. Okay, so that's the full picture. Yeah, so basically invert about A. Let me check the chat. Yeah, consider the inversion with radius AH times AG. So yeah. So basically, FH, we have a whole bunch of, so yeah, so phi swaps BC in the circle with diameter AH. So, so phi takes R to T, S to V, and L to U. So, so showing that R, L, and S are collinear. It's the same as showing that T. So I'm trying to think. So that's equivalent to showing that TV, AT, WV is cyclic. Oh, because inversion of a line passes. So the line passes through the point at infinity. So the inversion would go through A. So phi takes R to T, L to W, and S to V. So R to T, L to W, and S to V. And then we do the angle chase. So angle AVT. So that's just 90 minus angle VAG. So it's 90 minus angle OAG, and it's not hard to see that that's equal to angle, which is 90 minus OAG, which is 90 minus ODA. And that's equal to angle OWD. Or I could say, so 90 minus ODA is yeah. So I want to show 90 minus ODA is OWD, but OWD is the same as ODW, right? So wait, but those don't add up to 90. Somewhere I did something wrong. Let's see. OAG. Let me check the chat. Oh, we didn't prove yet that DW and T are collinear. So okay, I'll just copy that angle chase. So I agree, we should prove that DW and T are collinear. Oh wow, have we already been doing this for an hour and a half? Yeah, this is the first one. Okay, let me. You know what? I'll just quickly just write in the details and then maybe move on to the next one. Because yeah, I want to get to more problems. Although this is a good one. Oh no, I'm sorry. We've only been doing it a half hour. I don't know. I thought we did it a full hour, but yeah, no, we have time. So oops. So this means that A, B, WT is cyclic. Let's see. And that means that R, E, and F are collinear, or R, L, and F are collinear. And that means, or R, L, and S. And that means that BP, CQ, and RS are concurrent. BP, so now I'm going to read what you wrote in the chat because I know I didn't. There are a couple of things I skipped here. So let's see, AVT. That's 90 minus OAD. And OAD is basically half of, so AOD is twice angle C. So that should be 90 minus B plus C. That looks correct. That should be correct. Okay, so let's see. Whoops. Okay, so Sardar just posted a generalization of this collinearity right here. So T, D, and W. But maybe it's just a radical axis theorem, because let's see.
I have a proof for this. Just
Okay.
using the similar triangle.
That T, D, and W are collinear?
No, I mean Q, L, and C, I guess.
Oh, Q, L, and C are collinear?
Yeah.
Oh, that's yeah, this part right here. So thanks for joining, Sai. So what's the proof using similar triangles?
Could you just draw the QC?
Okay.
Okay.
Whoops, sorry. QC.
Yeah.
All right.
Yes. So we note that if we call QC cut EF at the L prime at the point L, we will prove L is the midpoint of EF.
Okay.
Okay, so triangle LEC, yeah, is similar to FHD.
FHD. Okay. LEC is similar to FHD, and that's probably just an angle chase, right? Yeah.
Yes. So we got FH over HD is equal to LE over EC.
Mm-hmm.
Yeah. And then yeah, you if you write it, it will be easier to look.
Okay, so FH over HD is LE over EC.
Yeah.
All right.
Okay.
All right.
Okay, but we have that triangle FHG.
Mm-hmm.
Is similar to GG. That point. FHG is similar to FEC.
Ah, okay.
Yeah. So FH over HG is equal to FE over EC.
All right. So FHD. FHD is similar to LEC.
Yeah, LEC.
And let me. Whoops, I put that twice. Maybe I'll just write it like right here, and then FHG is similar to FEC.
Yes.
And I'm trying to see if that works. There we go. So that means that FH over HG is FE over EC. And then we know FG equals G, or I'm sorry, HG equals GD. So if we combine these, then we get F. Actually, I should call this L prime everywhere. So implies FL prime equals L prime G. So why don't I could put a star by this. And so I'll say let L prime equal EF what is it? QC intersect EF.
The last one is L prime F equal to L prime A, not L prime G.
All right.
Yes.
L prime F
E.
L prime E.
Yes.
All right. See how this comes out. Whoops. Okay, so I'll just leave this over there. Why not? Okay. So so this proves that fact, and then for D, W, and T are collinear. So T, G, B, and C are in harmonic conjugation. I think that's well known because yeah, I mean, that's true because CF, BE, and AG are concurrent. So we know this is true. And then if we project from D onto the circle, then we get Q, P, W, PG, B, so BC, oh, but W, so what, I'm sorry, A, B, C, W. So basically we want to show A, B, C, W are in harmonic conjugation. But if we project onto EF, it would be, so we draw the tangent at A. Sorry, it would be ELF. Oh, because the tangent at A is parallel to EF. So if we project A, B, W, and C onto EF, then we get ELF and infinity, which is -1. Okay. I think I'll just move on to the next problem right now. I think I understand this proof right here that D, W, and T are collinear.
Michael, could you explain part B again? I joined a little bit late, so by reading it, I can't go through it.
Oh, it's all right. Yeah, there's a lot to it, but I'll just try to do it quickly. So first, we want to show that if L is the midpoint of EF, then we want to show that BP and CQ intersect at L. So here's Feng's idea. So what we do is we let CQ intersect EF at L prime, and we want to show that L prime is actually the midpoint of EF. And then he found two different similar triangles, and then he combined the ratios, and he found that L prime F was L prime E. So L had to be the midpoint of EF. And so that means that CQ intersects EF at the midpoint. And then we could use the same argument to show that BP intersects EF at the midpoint. And so CQ and BP intersect at the midpoint of EF. So that was just this first part. And then the second, and then if we let AL intersect a circle at a point W, and we let EF intersect BC at point T, then you can prove that P, D, and W are collinear using some projective geometry. I talked about it, but I don't think I'm gonna write it all out. And then I used inversion. So we found an inversion about A that swaps B and F, H and G, C and E. And that inversion, it takes L to W. And it takes, so yeah, we want to show it takes R to T. So it takes R to T, it takes S to V, takes L to W. So showing that R, L, and S are collinear, it's the same as showing that A, T, W, V is cyclic. And then we did an angle chase here, and that was pretty much it. So a lot of stuff went into it. I'm not going to go through all of it, but I will, you can ask me.
Not sure I completely understood it, but but if you could keep this page for a few seconds more, I will take a screenshot real quick.
Okay. Yeah, so you can take a screenshot. And
okay, done.
if you want,
Thanks.
so I email out all of these. I can put you on an email list where I send out the GeoGebra file for this. So then you could actually open it up yourself after the meeting.
Yeah, please do that. Thanks.
All right, you're welcome. So here's the next problem. This is also from Vietnam, 2 parts as usual. So we have a triangle ABC. It's inscribed in a circle O. All right. Let O be the center. And M is on arc BC, so that AM is, okay, so M is like any point on arc BC. Let me make this like a little bit more condensed. So maybe like this. That'll give me some more room. Okay, so and okay. So M is like any point on this arc that doesn't, so that AM isn't perpendicular. I think it was AM isn't perpendicular to BC. Is that right? Whoops. Oops, sorry. This almost looks like AM is perpendicular to BC, so I'll move it a little bit. AM meets the perpendicular bisector of BC at T. All right. There we go. Let me move M to be on the other side of the arc. There we go. So for the first part, this point right here is T. And the circumcircle of AOT meets the circle at point N. So yeah, the first part doesn't look as hard. It kind of looks a little familiar. We want to show angle BAM is equal to angle CAN. So we want to show they're isogonal, which is the same as showing that BN is equal to CM. This is probably an easy angle chase, I would bet, right? You guys are probably going to find it faster than me, but yeah. Let's see. So OA is equal to OB. So we want to use that fact, and they're both equal to ON.
Well, this is because OAT equals to ONT and OAT equals to OMT.
Okay, so OAT is ONT and it's also OMT. So then by symmetry, BN equals CM and they're isogonal. That makes sense. All right. Let me, all right, so that's part A. Now, let's see if we can do part B. So, but yeah, I guess maybe it's worth just drawing the midpoint of BC, just to show it's the perpendicular bisector. Let me call this J. All right. So that's part one. And then for the second part, let I be the incenter and G be the foot of the angle bisector. So okay, and then, oh, I want the incenter to be I. So let's say, I don't know, just call the incircle G. But it doesn't like that. Trying to figure out how to, why won't it let me rename this? Okay. I'll just call it Z. There we go. So I is the center of Z. There we go. And G is the foot of the angle bisector. So that's G. And AI, MI, and NI intersect the circle at D, E, and F. Interesting. Let's see, is that D? Yes. I don't have to rename the points. So let me move this all the way down, move this all the way up. So we have D, E, and F. And P is DF intersect AM. And then we draw DE intersect AN. I wonder if A is the, no, I don't think A is the midpoint of EF. This looks a lot like Pascal's theorem. So P would be, oops, that's point P. And this is point Q. And the circle that passes through P and touches AD at I. Oh, this is a lot of stuff here. Okay. So let me first make things look a little nicer. Before I go further, I'm gonna make the diagram clearer. Whoops. I hid A. So we have AD. What was I doing? Oh no, I don't want to draw that. I want, oh, is that everything I need? I think so. Oh no, AI, I need to draw these two. So I think PI and Q are collinear by Pascal's theorem. That should be true. And it looks like PQ is parallel. And I would guess that's probably not that hard to prove. So the circle passing through P that touches AD at I. So basically I want to draw the perpendicular so here's what I want. I want to draw the perpendicular at I to AI. And I want to see where does it meet the perpendicular bisector of PI and QI. And those would be the centers of those circles. So this point and this point, then I'll draw those circles and then I'll hide a bunch of stuff. So that circle and this circle. This is a complicated diagram. All right, so you draw those two circles. And it meets, so this one meets DF at H. So let me move this label out of the way. So it almost looks like, I don't want it to think H is on the in circle. So, okay. So this should be point H. And then the other H, I think we'll have to do some rename because And then this point is K. And then we want to show the so let me just rename these. So H1 I could call X and K1 I'll call Y. And we want to show the circumcircle of GHK is tangent to BC. All right, let's check the chat. That's not K, that's the inner, K is where the circle meets DE. Oh, you're right. So I can delete that point and I can call the other one K. There we go. So we want to show the circumcircle of GHK is tangent to BC. And do we really even need the in circle?
I think we don't need the in circle, so
okay.
Hide it.
We can hide it. Yeah, I just created it to make the end center. So PQ looks parallel to BC. Yeah, so we know PI and Q are collinear by Pascal's theorem. And then the fact that it's parallel, is that like an easy angle chase or something? Whoops, sorry about that. Hold on just a second, guys. One second, I'll be right back. All right, I'm back. Thanks for waiting. Yeah, a lot of points here. So x, I, and y are linear and perpendicular to AD. We know that. I can close this for now. There we go. So yeah, really, we can hide point T, right? We don't need, we know that AN and AM are orthogonal. So yeah, we can hide that. I mean, we could keep point J in there if we wanted, but I'll just hide it for now. Yeah, but we don't need the circumcircle of AON. So Pascal on DDFNMA. DDFNMA. Okay, because N and M are symmetric about OD. Let me hide this little section right there. There we go. And so basically, PQ and the point at infinity, the PQ and the point at infinity on the tangent through D are concurrent. So PQ has to be parallel to BC. All right. That makes sense. Because DD and BC meet at the point at infinity. Okay, so All right. I feel like now that I hid some stuff, this problem's looking a little less scary. I don't think these concur, do they? Those three? No, it just looked like it. It was an illusion. Okay. All right, looks like Anmol is joining us. Hey Anmol, it's been a little while. Thanks for joining. So we are on our second problem from the Vietnamese Math Olympiad. And these are some really nice but tricky problems. So each of them have two parts. So we just started on this. We started on this one. We solved part A already. And for part B, we made a little bit of progress, but we're still working through it. Let me move things down just. Hello. But yeah, the first problem was really fun. So yeah, I'm glad Feng suggested this contest. All right. I wonder if the circumcircle GPQ is tangent. No.
Michael, I think we should prove QB is parallel to BC first.
Oh yeah, so Hakan had a proof for that. So if we use Pascal's theorem, basically Pascal's theorem can prove it. So he used Pascal's theorem on dm or ddmnef. So basically consider, so we have FENDDM, right? So we count like D twice. So DE, oh, but I feel like, hold on one second. Let me read what he wrote in the chat one more time. Oh, DDFMNA. Yeah, so.
Hi.
Hey, thanks for joining. So yeah, we got a lot of people here now.
Hello. Can you hear me?
Yeah, I can hear you.
We want to prove IP is parallel to BC, right?
Right.
I think that it is really easy by proving that AIPF is cyclic.
AIPF is cyclic. Okay.
Yeah. And that is easy because AIF because AIF is equal to AF plus DN arcs. I mean AF plus DN over 2, and we know that DN is equal to DM, so it is really easy to see that AIF is equal to APF.
Okay. So we have two different ways of doing it then. So we have Pascal's theorem.
And after that, yeah. And after that, AFI is equal to AMN, which is equal to API. So PI is parallel to MN, and it is parallel to BC.
All right. So it looks like we have two different ways of proving it. So we have this way. So we prove that this is cyclic, AIPF. And you mentioned that you did that using arcs. So so say one more time. So I think you showed that angle AFP is 180 minus AIP, right?
No. I show that AIF is equal to APF.
AIF is APF. Oh, because they're both half of the intercepted arcs. Yeah. So
yeah,
AIF is half of. Okay. I like that. So that avoids having to use Pascal's theorem. It's pretty nice. So yeah, I think when I type it up, I'll do that proof just because it avoids Pascal's theorem. or maybe I'll just write both, but yeah. I like how you use that the angle is half of the two intercepted arcs. That makes it look like really clear why it's true.
Yeah, and after we have PQ is parallel to BC, we yeah, I got the proof that use the inversion.
Using inversion?
Yeah.
Yeah.
D.
Yeah, I think inversion will be useful.
Okay.
Yeah, it will solve the problem. We will use the inversion with D and with the ratio DI square.
Di with radius di, because di is equal to db is equal to dc.
Yeah.
And so the inversion, it looks like it takes k to q and h
Yeah.
to p, right?
Yeah, and G to A. So the line, so BC will become the circumcircle of ABC.
Mm-hmm.
Yes, and
Yeah.
the circle QPG is A. No, GKH is to AQP.
And then we could use homophogy to finish it. Ah,
Yeah.
very nice. I like it. All right, so I'm going to type it up. So for part A, we basically have two ways of solving it. So I'm gonna just briefly mention both. All right. All right. Let me make as much room as I can. I'll just make my life easier later. Okay. So for part A, oops. There we go. So we have angle ONT is OAT is OMT. And that's angle OMT. And so from there, we know by symmetry, N and M are symmetric across OD. And once we know that, that means that angle, that means that BN equals CM, which means those two angles are equal. And then for the second part, by Pascal's theorem on FAEN dm, we have QI and P are collinear. And then after that, there's two ways to proceed here. So first I'm going to show the angle chase. So we have angle AIF is half of AF plus half of BN. That should be good. And that's half of AF plus half of DM. Sorry, copy paste doesn't work that great in GeoGebra, so I'm just rewriting it out again. And that is angle APF. So AIPF is cyclic. And that means, and then we have angle API is AF, AFI is AFN. Whoops, I'm going to fix that later. But for now, we have the angle API equals angle AFI is angle AFN is angle AMN. That means that PQ is parallel to MN, which is parallel to BC. So this should work just like that. Here I just have to add that. Let's say why does this look so weird? I think I have to, there we go. I could say or use Pascal on FAN-BDM. All right. And then once we know that, consider an inversion centered at I with radius. So first I'll use the in-center x-center lemma. So by the in-center x-center lemma, dB equals di equals dc. And then consider an inversion centered at D with radius di. And so it takes G to, it fixed, so I'll say phi fixes B and C, or phi sends BC to the circle O, or I'll just say BAC. It sends, okay. It swaps K and Q. And it swaps P and H. So I'm going to make sure in the end that I actually prove everything that I say. So basically, phi sends the circumcircle GHK to the circumcircle BPQ. So a homothety, by a homothety at A, wait, is that right? I'm sorry, it sends it to APQ. So by homothety at A, since PQ is parallel to MN, PQ is parallel to MN, means that the circumcircle of AMN is tangent to ABC. And actually I have more space here, so I could just make this one line. So if we undoing phi, then we have GHK is tangent to BC. All right. So it's still not obvious that this swap's tangent. Oh, DD, DDF, NMA. Okay. So yeah, the question is this step. Oh, because DI squared is DK times DQ. So all right, nice solution. So now I will move on to the next problem.
Excuse me.
Yes.
AMN is tangent to APQ.
AMN, oh, it's tangent to APQ. Yeah, you're right. Thanks for fixing that. So, yes. All right, looks good. So I will move on to the next one.